Hello, viewers, students, and future engineers. Here is another example on a determinate beam solved by three-moment equations, and there are support settlements. So for the beam shown, E is 200 gigapascals and I is 500 times 10 to the 6 mm to the fourth. Support settlements are A 8 mm, B 15 mm, C 10 mm, as indicated here, and D 6 mm. Compute all support reactions and enter the moments at B and C. So we use three moment equations here. So by the way, EI is 200 gigapascals, so 200 times 10 to the 6 kilopascals times moment of inertia 500 times 10 to the 6 mm to the fourth divided by 1000 to the fourth to convert this to meter to the fourth, and you will get 100,000 kilonewton meter square. We then write three moment equation on ABC. Remember that the moment at A is 0 and at D 0, these are end supports, pin supports, and ruler supports. So moment at A is 0 plus 2 times moment at B, then quantity L1, which is length of AB 8 plus L2 length of BC 5 plus moment at C times L2, which is 5, then plus 6 area 1A over E1 I1 L1. So we can use the formula WL cube over 4, so 28 times 8 cube over 4. Then 6 area 2B over E2 I2 L2 is 32 times B3 all over length 5 quantity L square 5 square minus B square 3 square equals 6 times EI 100,000 quantity. So remember the reference horizontal tangent is B, and therefore A is 7 mm above A because 15 minus 8 is 7 mm, and 7 mm is 0.007 divided by length of AB, which is 8, plus 8 sub C, which is in this case C is 5 mm above B, so therefore plus 0.005 meter over L2, which is 5. So simplifying, 26 MB plus 5 MC equals negative 2766.2. Call this equation 1. We then write three moment equations on BCD, moment at D0, take note. So we have MB times 5, length of BC, plus 2 times MC, quantity 5 plus 6, plus moment at D0, plus 6 area 1A over E1 I1 L1 for this load here, 32 times A, 32 times 2 over length 5, quantity 5 square minus 2 square, while 6 area 2B over E2 I2 L2, the centroid is closer, so 7 over 60 by formula W36 length 6 cube. Then equals 6 EI, 6 times 100,000 times quantity. The reference this time is through C, horizontal line through C. So B is 5 mm below, so negative 0.005 over 5. And D is 4 mm above that horizontal line, so positive 0.004 over L2, which is 6. Simplifying, we have 5 MB plus 22 MC equals negative 1376. Call that equation 2. Solving equations 1 and 2, we can now compute moments at B negative 98.677 and the moment at C negative 40.119 kilonewton meter. So we then compute the reactions. I call this AY, AX is 0, R sub B, R sub C, and R sub D. And we apply the moments here. We have clockwise to the left of B, counterclockwise to the right of B because moment B is negative. So it should be directed as shown. Same is true at C because the moment at C is also negative. So considering AB, summation moment about B equals 0, so we have AY times 8 plus 20 plus MB, which is 98.677, equals moment of the load 28 times 8 times 4. So AY can now be computed and it is equal to 99.665 kilonewtons. Likewise, we consider the reaction just to the left as RB left, summation moment A equals 0, RB left times 8 equals MB, which is 98.677 plus 28 times 8 times 4. So RB left is equal to 124.335 kilonewtons. Considering BC, summation moment C equals 0, RB right times 5 plus MC, which is 40.99119, equals MB, which is 98.677 plus 32 times 3. Moment of the load, 32 times 3. So RB right is equal to 30.912 kilonewtons. Likewise, we can now solve RB. RB is RB left plus RB right. So 124.335 plus 30.912. So RB is equal to 155.247 kilonewtons. We then consider summation moment about B, still BC. So RC left times 5 plus MB, which is 98.677 equals MC, which is 40.119 plus 32 times 2. So RC left is equal to 1.088 kilonewtons. Then considering CD, we call the shear here as RC right. Summation moment D equals 0. RC right times 6 equals MC 40.119 plus 1 half of 6 times 36 times 2, moment of the load. So RC right is equal to 42.686 kilonewtons. So we can now compute R sub C 1.088 plus 42.686. So R sub C is equal to 43.774 kilonewtons. Finally, considering CD, summation moment C equals 0, so R sub D times 6 plus MC 40.119 equals moment of the load 1 half of 636 times 4. So RD is equal to 65.314 kilonewtons. So to check, you just check it. Summation forces Y should be 0, and I already checked it, and it is 0. So that's it for this problem. I hope that you were able to follow the solutions and the explanations. And this is the applications of three moment equations with support settlements.